So before that, just calculate the value of VDS from this plot. From this figure, which is you will get the VDS value which is equal to V naught. So this is your VDS, which is equal to V naught. So when you apply a KVL into this loop, then what you are going to get is minus VDD plus ID into RD plus V naught is equivalent to 0, right? So to calculate the value of V naught, which is equivalent of VDD in our case, so VDD plus ID into RD plus VDS is equal to 0. Now we calculate the VDS value, which is equivalent to VDD minus ID times RD. So to know the value of VDS from this figure and then value of resistances that is given to us, first we have to know the value of ID. And that's the reason where we are assuming that the transistor is under saturation region of operation, and then we try to take the saturation current, ID in saturation. Okay. Now if I write the ID expression in saturation ID expression I am writing here, which is half mu n COX W by L VGS minus VTH whole square, because channel in the modulation factor which is given to us is equal to 0. So you need not to add that part. If it is given lambda value is some x, y, z, then you have to take that lambda into the consideration and then extract the ID value. If you neglect it, if the lambda value is given, then your calculation goes wrong. If lambda value is 0, then accordingly substitute the formula and get the value of ID. If lambda value is given, then take that lambda value and try to extract the ID value. Okay, so half mu n COX is 100 micro, so 10 power 6. W by L is 10, and VGS, how much it is? VGS is 12 volts, 1.2 volts minus VTH is 0.5 whole square. Now we substitute all these values, then you will get the current, which is referred to be 245 microamperes. This is what the current that you can obtain. Okay. Now this current is obtained, and what you have to do is now you calculate the VDS value, because in VDS expression VDD minus ID times RD. So RD is available to us, VDD is available, and we have calculated ID also. Then take the VDS value. So VDS, which is equivalent to, now you substitute all these values, then you will get the VDS value is equal to 1.265 volts. So this is your VDS value. Now from this actual value of VDS, and then you calculate the VGS minus VTH, which is equal to VDD from these assumptions, then now VDS, which is equal to, that should be greater than VGS minus VTH. What is this value? So you will get is 1.2 minus 0.5, which is equals to 0.7. Now this is what actually a minimum value that you require to make your transistor in saturation. But what is the value you are getting, which is higher than 0.7? So the assumption that we made, VGS, the transistor in the saturation region of operation, which is correct. How we verified? We calculate the VDS value by substituting ID current and RD values, and we come to the VDS value, and we are aware that VDS is greater than VGS minus VT. 1.2 is VGS, 0.5 is threshold voltage, and which is coming to be 0.7. So your VDS value should not be less than 0.7. Okay, it should be greater than or equal to 0.7, but we are getting 1.265. So which is well above this VDS value, and hence the transistor is under saturation region of operation, and the current that we extracted is correct. Okay. So what are the assumptions we made, which is correct now, right? Now we have to calculate the GM. What is the transconductance of this circuitry? So we can use some of the formula for GM. So we had seen 3 equations for GM, which is mu n COX W by L, VGS minus VTH is one formula. Second one is 2 ID by VGS minus VTH. Third formula and second one and third one is under root 2 times ID mu n COX W by L. So using these 3 formula you can substitute it, but you have to take the formula which is more convenient to substitute the values. So we already calculated ID, we already known to the value of VGS minus VTH, then we take this formula so that we can easily substitute the values. Okay. You are aware that the value of ID, which is 245 microamperes, VGS minus VT value and 2. So just substitute it, then you will end up with getting the value of GM, which is equal to 0.7 millisiemens in terms of resistance, which is 1 over 4.3 kilo ohm. Okay. This is the second parameter that we are calculating. The third parameter that we have to calculate, which is gain of an amplifier AV, which is referred to be minus GM times RD parallel with R naught. So R naught is given as 0. So then formula is this one. So GM is known to us, RD is known to us. Just substitute the value. Then you will get the AV, which is equals to minus 2.1. So whatever the signal that you apply, the signal is getting amplified twice of your input, 2.1 times. But generally, doubling of your amplitude of the signal is not referred to be great amplification. Of course, it is amplification, but not a great amplification. So at least you require 10 times or 20 times of your input signal that you apply, so that you'll have more amplification in your signal. So we are not satisfied with this amount of amplification, then we are trying to get more amplification in it. So we have the two parameters here, which is GM and then RD. What you can do is you can increase one of these two values and you can increase the AV. Right? So there is a two possibility here, GM and RD. Let's go for first RD and making GM as constant. So assume that GM is constant and we increase RD. What is RD? RD is a load resistance value. If we increase the load resistance value, then you can ultimately increase the gain of an amplifier. Okay. So assuming that instead of 2.1, we are trying to double the gain. So instead of 2, we want to make it as 4. So whatever the value we are getting now, we are not satisfied with that. Now we want to double the gain that we are getting now. Okay. So instead of 2.1, we are expecting that it should supposed to be 4.2. Okay. To do it, then what you have to do now, what is the value of RD? That the value of RD should be doubled. Then you will get the gain. Okay. Now if you do that, then what is going to happen? If battery is fixed, okay, then VGS and W by L ratio is fixed, and what you can do is you can check the bias condition if ID transistor is still under same region of operation, and then you can substitute these values and try to get the current. But when you see this VDS expression, which is referred to be VDD minus ID times RD, as this RD value increases, now we can say this RD value is increasing, then this VDS value is going to be drops, because net value of VDS is VDD minus ID times RD. As RD value increases, the drop from your VDD is going to be increases, and final net value of your VDS getting decreases. There is a possibility that because of decrement in your VDS value, then your transistor may enter into the saturation region of operation. Okay. So what we are trying to do is, now we make RD instead of 3 kilo ohm, now we make it as 6 kilo ohm. Okay. And then calculate the current. And current ID is remain constant. Okay. We consider that current is constant and W by L is constant. And just change the resistance value, which is twice the actual value, so that from the gain formula, we can see that the gain can be doubled. Okay. So now we calculate the value of VDS from the formula, which is given here, right? This one, which is VDD minus ID into RD. Now RD is doubled. So VDD, how much it is? 2 volts. Now ID is 245 microampere into 6 kilo ohm. Now this term is going to be increasing. So now you end up with getting the value of VDS is equivalent of 0.53 volts. What is the minimum VDS you require? Minimum VDS required should be 0.7, which is VGS minus VTH. So VGS is 1.2 and VTH is 0.7. So VDS should be greater than or equal to 0.7. This is what you require. But what is the actual value you are getting here is 0.53. It means transistor is under saturation. Instead of saturation, it is going in linear region of operation. Right? So you cannot use the gain formula that you are talking about. This one minus GM times RD is not valid, because this formula is valid when the transistor is acting as a operating in the saturation region of operation, and in saturation region of operation there is more amplification. In linear region, your transistor acts as a resistor, not an amplifier. Okay. Now then, what is the way out? So because of this, transistors enters into triode region of operation or linear region of operation. Okay. So transistor enter into linear region of operation, and then you cannot do that. And as we are well aware that as the technology is scaled, okay, as technology is scaling, you cannot make VDS value is constant. Okay. So there is one way that here if we increase this VDD value by decreasing this RD value, then you can compensate that effect. But nowadays what we are doing is, as we are scaling the technology, then you cannot increase the value of VDD. You have to decrease the value of VDD. If you decrease it, then further VDS value going to be drops further higher. So decrement in your VDS is going to be more instead of maintaining constant, because as technology scales, VDS value becoming smaller and smaller for lower and lower technology nodes. Right? Then what is the way out? Now only the other possibility that now you can see that this is one option and this is second option. So we tried the first one, it is not going to be work out, then take the second one. Now if we increase the GM, increase GM. If you increase the GM, then you have to check the sum of the formula for the GM. Now let me take the formula for GM, which is twice the mu n COX W by L VGS minus VTH. Okay. No, this is not the formula. That is actually it is ID. Now here you have two parameter. One is ID and then W by L. Now if you increase the W by L, then you can maintain the ID should be constant, or you increase ID and maintain the W by L should be constant. Then only you can increase the value of GM. To increase the GM, then you have a two option. One is W by L, another one is ID. If you are increasing one parameter, then other parameters should be constant. Okay. If ID goes to be higher, which results into again the transistor enter into this linear region of operation, because as you notice this formula here, as ID increases, then you talk about VDS, which should be VDD minus ID times RD. So here either increment in your RD or increment in your ID, which results into the same factor. Because they are multiplication of both, then the VDS value again drops down. So which is not a good sign. It means you should not increase the ID value, because increment in ID results into decrement in your VDS. Now transistor enter into the linear from saturation, which is not advisable choice. Then make ID is constant and then increase the W by L so that GM can be increased. Okay. If you try to do that, then as you increase the W by L as much as you can, increase the W by L as much as you can, and you will end up with getting the increment in your current. So now if you write the current ID expression, which is half mu n COX W by L, right, into VGS minus VTH. What we are doing is we are trying to increase the value of W by L, and you have to maintain this parameter. If this parameter is treated to be less, if this value is increasing and this constant, then ID is going to be increases. But our condition is that ID remains constant. How do you compensate? Increase the W by L and decrease this VGS minus VTH value so that you can maintain it. Okay. But as much as you can make wider and wider transistor by increasing higher value of W by L, and you will end up with getting the maximum GM value. The maximum GM that you can obtain by more and more increment of your W by L, which is ID times, which is roughly approximated as ID by 1.5 times of VT, and this VT is the thermal voltage. Okay. What is thermal voltage expression? Which is referred to be Kt by Q at room temperature, which is 26 millivolts. Okay. So now Gm is limited with ID value. You will make ID constant and 1.5 times 26 millivolts, right? Finally, you will end up with limiting of your Gm. Okay. So as you increase the W by L ratio of your transistor and you limit your GM value to certain, which is ID by 1.5 times of this. So now ID is 245 microamperes divided by 1.5 into 26 into 10 power minus 3. Now you can consider this is into 10 to the power of minus 6. Now if you calculate it, then you will get certain value of GM, which is limited. So this gives us not a perfect solution to increase the GM of your circuitry. Then what you have to do? Then you try to change the configuration from common resistive load to another load. Okay. So what we have been doing so far is that we are trying to increase the value of RD, are trying to increase the value of GM. So what we have tried is, once we tried for incrementing your RD, and other time is we are trying to increment your W by L ratio, then we limiting your GM value because gain of this amplifier is limited by minus GM times RD. So none of the solution is perfect. Then we have to switch for the alternative ways to replace this load element. Okay. And one more reason for going for other alternative is that when you are trying to increase a more and more resistance value, then IC fabrication is not suggestible to choose more and more resistor value because it consumes, it dissipates a lot of heat as well as it occupies more area. So for IC fabrication, more RD value is not suggestible to use to enhance the gain of your common source amplifier. Okay, this is one of the solution that to be identified. Then just replace this resistor with another element. Now what we are going to do is we are replacing with a passive. So resistor is your passive element. Now replace your passive resistive element with your another element, that is another passive element. This is R, and now you just replace with your diode D. Okay. So now you need to fabricate diode separately and then you want to replace it. Instead of that, just take a MOS transistor and then make MOS transistor is equivalent of your diode. This is your NMOS transistor, drain terminal, gate terminal and source terminal. You can make this MOS transistor as a diode by connecting gate terminal and drain terminal together. So if you connect drain and gate terminal, then what is going to happen is that this MOSFET is acts as just like your diode. Right, so now you can replace this component here and try to analyze the performance of your amplifier, because this MOS transistor doesn't require more area to fabricate and it does not dissipate a lot of power. Okay, so some of the problem can be compensated or minimized by taking this diode connected MOS transistor. So acting as a diode connected device, but it is a MOS transistor. MOS transistor based diode connected load that you have to replace it. Okay, but before taking this circuitry, then you have to analyze the small signal equivalent of this transistor, because we are well aware that this, now you talk about the gate to source voltage here, VGS value positive and negative here, and this is VDS value. Now if you consider that here VGS is equivalent of VDS, both are same. Now if you draw this small signal model for this diode equivalent MOSFET, then this is your gate terminal, this is your source terminal, negative, and here positive, which is VGS, and here you have GM times VGS, and this is your R naught, this is the drain terminal, right? What we have done in case of diode connected load, gate terminal is connected to drain terminal, so these two are shorted, right? Now if you short these two, what is going to happen? When it is shorted, When it is shorted, then what you can see here is that now your this circuitry is having here current called as ID, okay, which is going through this. And now if you write the KCL at this node, then what you can see here is that ID, which is equivalent of GM times VGS plus VDS by RD. Instead of R naught, if you write it as RD, then it is RD. Now VGS and VDS both are same. What we try to do is just replace VGS, which is equal to VDS. So ID, because in terms of drain voltages and drain current, we are talking about GM times VDS plus VDS by RD. Now if you rearrange the terms, then what you can see is that VDS by ID, which is equivalent of 1 over GM parallel with RD. This is what you can see that. And this is referred to your equivalent resistance, right? So we just replace this previous resistor with a diode connected MOSFET, and then this diode connected MOSFET resistance equivalent, right? So this is what your resistance equivalent of your diode connected MOSFET. So when there is small signal model, then you write this GM parallel with RD of that MOS transistor. If it is M1, then you write it M1 and RD1. If it is M2, then write M2 and RD2. Then you can analyze the performance of your circuit. So this is what your equivalent model, a small signal equivalent model for this, and which is resistor. You can consider this two terminal device acting as a resistor. Okay. So now if you consider that example, so here we are eliminating the resistor and connecting a diode connected MOSFET. So let me draw the M1 transistor, which is the basic transistor, and then small signal DC biasing. Source terminal is connected to ground, and here you have the MOSFET, which is source is connected to drain terminal of this M1 transistor. This is M2, and both are connected to same terminal, because as it is depicting this one, and this is your VDD, and from this point you can tap the VO. This is what the replacement of your resistive load with the diode connected MOSFET. Okay, and this is your VI, and this is your VGG signal that you're trying to apply. So this is a gate to source voltage VGS1 of your transistor M1. Now if you do the small signal equivalent model for this, then what you can see here is now for a small signal model, all DC sources are connected by ground, and this is equivalent of a resistor. If I write it the same, this is GM2 parallel with RD2 or R02, which is connected to ground for a small signal model. And here we have a small signal model, the transistor. So this is the drain terminal of the first transistor. So drain terminal of first transistor, and which is going to have GM times VGS, and here R01, this is V out, V input, this is VGS, right? So this is what you can see the small signal equivalent for this given circuitry, because this is equivalent of this MOS transistor equivalent of GM parallel with R02, and then the first transistor M1 is made as small signal equivalent. Now these two resistor, this resistor is connected between source small signal ground, this is ground, and this is also AC small signal ground. So these two resistors are going to be in parallel. Now what you can see here is that this is what you can see. GM1, VGS, R01. Now this is going into the resistance equivalent. This is GM2 parallel with R02. This is your V0. And this is AC ground. Positive negative, this is VGS, right? Now if you try to estimate the value of your gain, which is going to be V out, V out is given as minus GM1 times VGS into, it is two resistor equivalent resistance, because both are resistor. Now what you can do is just make the parallel resistance of these two. So R01 parallel with GM2 parallel with R02. This is what you can see, right? And VGS, which is equal to V input, so you can replace this as V input. So V out by V in is equal to minus GM1 into R01 parallel with GM2 parallel with R02. This is what the gain of your circuit. Okay, so which gives you the AV value. Then we have to calculate RI also. So now you calculate the RI value, which is going to be here, input resistance here at this position, RI value. So when you talk about this RI here, so gate to source voltage is 0, then you will get RI value is open circuited, RI value is going to be infinite. And coming to your R0 value, when you are talking about R0, then input side small signal equivalent is also considered to be 0, and then from output side apply the uh, uh, another source and then try to extract the current, and then finally you will get the resistance, which is referred to be R0 parallel with 1 over GM2 parallel with R02, because when you take this circuitry, then this input V input is equal to 0 here, which is going to be 0, and this is going to be 0. So nothing is available here, only this component is available to you. That's why we are writing here R0, which is the resistance available at the output side is R01 parallel with 1 over GM2 parallel with R02. This is what the gain of output resistance of your circuitry. Okay, Kartikeya.
Sir?
Shall we add section B people?
Yes, sir. Just join the other link, sir.
Sir,
Yes.
sir, shouldn't it be 1 by GM2 in the above steps?
One second. Yes. Gain equation, right?
Yes, sir.
Yes, you are correct. Actually, here I have written it in R0, but look at this one, which is 1 over GM. Sorry, here 1 over GM2 parallel with R02. Okay. Yeah, thank you for the correction. Kartikeya,
Sir,
is my screen visible to you all?
for A section, it's visible, sir. For B section, Hemant will respond.
For B section also it is visible.
Okay, sir.
Okay, fine. Yeah. So, so far we have been discussing about how to boost the gain of an amplifier, and we had seen, common source stage with resistive load, and this resistor is replaced with diode connected MOSFET. And we had seen the gain as well as input resistance and output resistance of an common source amplifier, right? Now, what we try to do is we just take an another different load element instead of resistor and diode connected load, and we'll choose other element, and then how the gain is going to be modified. Okay? We'll take common source stage with current source. With current source. Okay. So current source is a load element that we normally choose, and this load is DC load. Okay. Of course, you can make this current using MOS transistor also. Current source, MOSFET can act as a current source when it is operating under saturation region of operation. If you fix the voltage, VDS voltage, then you will not tune the voltage further, then it acts as a constant current source. You can use it, the constant current source, for your analysis part also. Now we are not going to do that. First we try to analyze with ideal source, and then what is going to happen. Okay. First, let me draw this is current source, which is connected from VDD and drain of your MOSFET. Okay. This is I1 that I can consider, and this is a V0 we are talking about. This is the ground terminal, and this is M1 transistor. Of course, here, we can apply the small signal as well as the biasing voltage. So this is the biasing voltage that you apply, VGG or V0, and this is VI signal that you can consider. For a small signal model, what you can do is just consider only this small signal, because all DCs are connected to ground. This I1 is, we are talking about DC current source. You can make this DC current source with the help of a MOSFET, which is referred to be, and the MOS transistor under saturation region of operation, and assuming to be there is a body biasing effect, not body biasing, channel length modulation factor. Then you can write I1 expression is half mu n COX W by L VGS minus VTH whole square into 1 plus lambda times VDS of a transistor if this is replaced with a MOSFET device. But if it is ideal current source, okay. So in case of ideal current source, what you can do is you just remove this element, because ideal DC sources are treated to be zero in small signal model. That is what we have done in the previous analysis part, and then we analyze the gain of an amplifier. Now if you do that, so DC sources are connected to ground, and we are assuming that this is our DC source, not a MOSFET based current source, just time being considered as DC source. So if it is so, then what you can do here is that take a single MOS transistor which is available to you, and here you try to apply V input, and this is grounded. Now what you can do is this MOS transistor along with the channel length modulation factor, you want to account it, that you can write it parallel to the drain to source terminal, and source is connected to ground. Can we write it? Because here the current, you can write it as GM times VGS. As VGS changes, then you have this value, and this is what your V0 terminal that you can write it precisely. Okay. What we have done is that the MOSFET is considered to be an ideal source. Sorry, the current is referred to be an ideal DC source, and its equivalent resistance is not considered. DC current source have a different way of representation, but For our small signal model, we consider the DC source is connected to be ground, and that's why we have connected to ground directly. And then MOSFET, put a wait chair, half an hour. So what you can do is that you just take this MOS transistor and then its small signal model and then try to analyze it. Or else what you can do is we just consider this gate and the gate to source voltage VGS. This is R0. So this is GM times VGS. Now we are representing in the transistor itself symbol. In transistor symbol itself, we are trying to indicating it is this is R01 and this is V0. And source is connected to ground terminal. This is what it is depicted. Now if you calculate the V out here from the transistor or small signal equivalent model, which is equivalent of minus GM times VGS into R01, because resistor is parallel with GM times VGS. And now what you can write is VGS, which is equal to V input, V0 by V in, which is equals to minus GM times R01. This is what the gain of your circuitry by considering DC source. Now what you can consider here is that this GM is written as capital GM. This R0 one can be written as capital R out. Okay, we are assuming that GM is capital GM and then R0 is equivalent of capital R. Now what we'll do is now we'll replace this ideal source with a MOSFET and then we use a P MOSFET. Okay, here gain is high in comparison with your other load element, because when you talk about other element they are coming in parallel and other way and your gain is going to be dropped down. But in this case, when you have an ideal source, then your gain is going to be depends on only the GM value and then this R0 value. If R0 value is not there, then it is depends on the only GM. Right? So what you can do is you just use the practical device instead of ideal current source. Okay. So to make your current source with the help of PMOS transistor, then what you have to do is take a PMOS transistor here. So let me draw first nmos transistor. Which is connected to V input small signal and this is ground. Here we'll tap the output. And then we'll take a PMOS transistor, something like this. Now here the current is flowing in this direction and this direction. This is your M1 transistor, this is M2. Now what you have to do is you just bias the transistor. VB is a biasing voltage for your PMOS transistor and this is your VDD. This biasing voltage ensures that the transistor M2 is under saturation region of operation. Okay. There's a gate terminal, source terminal and drain terminal of your M2 transistor. Similarly for your M1 transistor, this is drain and gate and source terminal. Gate of your M2 transistor is connected to VB and VB is applied in such a way that your M2 transistor is always under saturation region of operation and it acts as a current source. Okay?
Still, sir.
Yes.
So why are we using PMOS transistor here?
You can use NMOS transistor also, but it is easy for us when you are talking about a CMOS technology, when we use both PMOS and NMOS transistor. You can use NMOS also. There is no big deal in it, but this is a kind of analysis. If we see that what is going to happen if with PMOS transistor, and then later part when you go for current mirror circuitry and differential amplifier circuitry, there you have NMOS and PMOS transistor. When we try to build a system, then we try to consider the circuits as a repeatable circuits. Repeatable nothing but when you have NMOS and PMOS transistor and you want to use it repeatedly in a same circuitry, then you need not to spend a lot of time to analyze the performance of the circuitry, because if you have combination of these two and then you analyze somewhere else and then you can bring it here and you can analyze your rest of the circuitry. It makes your job easy, right? So this could be one of the reason that your other circuitries of current mirror and the differential amplifier, there you are using PMOS transistor, and because of that reason you can use a PMOS transistor as a current source here also. Otherwise you can choose NMOS transistor and make your NMOS transistor or bias your NMOS transistor in a way that it acts as a current source. Okay.
Yes. Thank you.
Now what you need to ensure here is that here drain and then source terminal. So here you can consider VDSP, PMOS transistor, and it must be under saturation region of operation. Okay. And pretty simple way of representing the IDVGS plot. So this is how you can write the plots of your MOS transistor. Up to this point, you're going to have VGSP minus VTP of transistor, and this is your ID current. This is your VDSP of your MOS transistor, and this region will indicate it is under saturation region of operation. Okay. So if VGS of your PMOS transistor is fixed value, that is VD minus VDD. So now you fix this value, then now you're going to consider the VB minus VDD. Hence, there is no change in your small signal analysis because this is also DC and this is also DC, and there is no change in these two. Then you can, for AC small signal analysis, you can neglect these two terminal, and then whatever the GM available and other parameter, small signal parameter of your M2 transistor that you can take into account, and then you analyze the performance of your circuitry. So what you have to do is GM VGS for your M2 transistor is going to be 0 because gate to source voltage of your transistor is fixed, right? Because VB is fixed. Why do you fix your VB? To make your transistor into saturation. Now VB is this one and VD is this one. Now this is a gate terminal, this is a source terminal, this voltage is fixed. Now this voltage is fixed, then you can consider that M2 transistor in a small signal model is 0. Therefore, no need to consider the transconductance of your M2 while doing the small signal equivalent analysis. Okay. Then what is the other thing that we need to take care about this analysis part is that only the R2 R02 terminal which is available to you. So now if I draw the small signal equivalent for it, then what I can see here is that first let me draw the first M1 transistor. This is M1 grounded and this is your V input signal. So now I am not writing GM times VGS because your gate and source terminal both are same. So there is no difference in VGS. If there is no difference in VGS, then there is no GM in your circuitry, then you can neglect that part. That's the reason we are not considering this. This is R02 because of your M2 transistor. Along with this, there is, so this is upward, this is GM2 into VGS. Because here gate voltage and source voltage are same, then there is no difference in the gate to source voltage, then you can neglect this stuff. And that's why we are neglecting this factor, and for AC analysis it is connected to ground. And this is what your V0. And now if you take resistance here R01 and this is referred to be GM times VGS1, then you are going to have the analysis part of your circuitry. Now you talk about V0, which is equals to minus GM1 times VGS1, right? And now these two resistor R01 and then R02 are going to be parallel if you try to draw the small signal equivalent model. Let me finish it here. This is your gate terminal. This is the source terminal connected to ground. Then this is your VGS, positive and negative. GM times VGS1. This is R01. And now here it is a drain terminal. Now same drain terminal R02 connected to AC ground. So you can write it as R02 and this is your V out. Now from this analysis what you can do is that you try to calculate V out here, positive and negative V out. But you can write V out, which is equivalent of minus GM1 VGS1. Now these two are going in parallel, so what you can write it is R01 parallel with R02, right? Now VGS, which is equivalent to V input, that you try to apply here. So V out by V in, which is referred to be AV, is minus GM times R01 parallel with R02. This is what the gain of your amplifier. In place of your ideal current source, if you replace with a PMOS transistor and which results into, now in case of your ideal PMOS transistor, sorry, ideal current source, what we have the gain is that this is what the gain that you can notice, that is minus gm times R01. Whereas when we consider practical PMOS transistor, then gain is becoming R01 parallel with R02. If R01 and R02 are same, then what happened to our gain? AV value, which is AV by previous stage is AV, and now it is by 2, because R01 and R02 same, both are same resistor, then it is exactly half of this two, or average of these two. Now your net gain is going to be half of your gain of previous case, right? So you cannot use this sort of analysis or load element as a PMOS transistor by considering for improving the gain of your amplifier. Then you need to search for alternative ways how we can analyze the gain of your amplifier. Now we are talking about the gain of amplifier in a common source stage, right? So we have considered the resistive load, we have considered that diode connected load, and we have connected the ideal current source replaced with MOS transistor. When we are talking about ideal current source, then this is the gain. But when we replace this ideal current source with the PMOS transistor acting as a current source, then gain is becoming lesser in comparison with that circuit. So we'll move on to other configuration where we can analyze the gain of your circuit. So what we have to do is we have to move from common source stage to common drain stage. Okay, so let's talk about the other configurations where we can discuss the gain of your circuitry from common source to common drain and common gate configurations. Now we'll talk about this common drain single stage amplifier. Okay, then the common drain stage, single stage common drain amplifier is depicted or drawn, is going to be something like this. This is where you try to apply the inputs. Of course, I'm not all the time not drawing the DC supply, so DC biasing voltage, but you are supposed to draw the DC biasing here. So what you have to do is consider V input, biasing is applied and connected to ground. So this is your VGG that you try to apply. And this drain terminal is straight away connected to ground. And here you have the current called as ID, but the source terminal is not directly connected to ground. There is a resistor called as source resistor, RS is applied, and then we'll tap the output from this RS. So the ID current which is flowing through this transistor ID here, this one, the same current ID which flow through this resistor called as RS resistor. Okay, and here you have the gate to source voltage which is VGS. Now you can first you try to do the DC analysis, and then further you can move on to this small signal model, right? Small signal treated to be 0 and consider all DC voltages. So VGG, you can write it as VGG is equivalent of VGS plus V out. Why it is V out? V out which is equal to voltage across resistor RS, VS. Okay, so now I can consider this is the loop. This is the loop available to me, this one. Then I am applying it. So what essentially you can see is that this is what the VGG, I'm making small signal is 0, and here it is resistor. This is V out, RS resistor. Now this voltage is VGS, right? Now VGS is equivalent to VGG. Sorry, no, VGS is not exactly equal to VGG is not equivalent to VGS because there is a resistor RS is involved over there. So I can write it as VGG is equivalent of VGS plus V naught, which is equal to RS times ID. Okay, so you can write it as V naught, which is equal to RS times ID. So you write the current expression ID in, or else just replace the current expression over there. What you can see is that V out, which is equal to RS into, let me consider saturation current of mu n COX W by L VGS. What is VGS from this? What you can write it is VGG minus VGS, which is equal to VGG minus V naught, right? V naught is this one. So what you can write it as VGS, which is V input, that is VGG minus V out minus VTH whole square into RS, right? Now we take this factor, this entire term, this is going to be a K, and then rearrange them, then you will get the this is referred to be V out and this is V out, and arrange this term, you will get under root V out by K times RS plus V out, which is equals to VGG minus VTH. This is what you can see as you are as you try to draw the plot of V output versus V input. This is V input and this is V out. Then when V input is equal to VTH, V input is equal to VTH, then you are going to see nothing. When it is crosses this VTH, then you can see the linear variation in your V input and V out. This is a point called as VTH. Okay. Now what you can do is you try to make the small signal equivalent for this circuitry, and then analyze it for gain calculations. Okay. So V input, which is treated to be VGS plus V out. Okay. Now if I try to consider a small signal equivalent for this, this is referred to be V input, RS, V out, or node resistance is coming over here, and then this is connected to ground, and here we have a current called as GM times VGS, and this is what your VGS that you apply. Okay, so V input, which is equal to VGS plus V out in small signal mode. V out is always less than V input. Now you see that, notice this expression, V input and V output. Now what you can see is that V output is always less than this V input signal. If VGS is equal to 0, then what you can see is V input is equal to V output. So what you can consider is that V output is always less than V input. And now you take V output by V in, and definitely gain is going to be less than 1. And maximum you will get gain as equal to 1, not higher than that. Okay. Now when the gain is going to be less than or equal to 1, then do you call it as an amplifier? Because it is not going to amplify your actual signal. In fact, your output signal is less than the input signal, and there is no amplification take place over there. So what you can consider is that this is not actually an amplifier. Okay. The output voltage is following the input voltage with a small difference of your VGS, because your V input is equivalent of VGS plus V out. So the output voltage is following the input voltage with a small difference of your VGS. Hence we call it as a source follower. Okay. So common drain amplifier normally treated to be a source follower. You should not call it as an amplifier because the gain is not so high. Maximum you will get 1. And we are taking the output of your why we call it as common source is that because we are taking output at the source of your configuration, and we can write the V output expression for a small signal model is that P out is Rs in parallel with R naught into Gm times VGS that you can see. Okay. Now V out, which is Rs parallel with R naught into Gm. What is VGS? VGS is V input minus V out. Just now we had seen that V input is equal to VGS plus V out. Now you write the VGS value, which is V input minus V out. So V out, and take the V out common, then you'll get 1 plus Gm times Rs parallel with R naught is equivalent of Gm times Rs parallel with R naught into V. Now we can write the AV expression here. From this, let me write with this one. So from this you take this V naught by V in, which is equivalent of Gm. So let me write it here. V naught by V in, which is equivalent of Gm Rs parallel with R naught divided by 1 plus Gm into Rs parallel with R naught. This is what the gain of your circuitry, and you can see that the gain is not so high here, and this AV gain is less than 1. And here gain is the output voltage V naught, which is not getting 180 degree phase shift. It is not going to get 180 degree phase shift. You will get the same phase. So here we cannot write the minus sign over there, because the same, if it is input is something like this, then your output is also going to be something like this. In fact, these two are almost the same, because your gain is going to be maximum of 1, right? Now if you calculate the resistance, output resistance of this circuitry and input resistance, then what you can see here is that R out, which is referred to be, let me redraw this configuration. For R output stage, what you need to do, input should be grounded. This is your Rs, and this is grounded, R naught, and this is V out. This is what you can see. Now this is the current that you can see is Gm times VGS, positive, negative, this is VGS, and this is what your V output that you can see. And here we apply a Vx voltage, and then correspondingly we try to get the Ix value. So here VGS, which is referred to be minus Vx, okay, and Vx is equivalent of Ix plus Gm times VGS into Rs parallel with R naught. Vx, which is referred to be Ix Rs parallel with R naught minus Gm into Vx Rs parallel with R naught. Just divide it, and finally you write it like I R out, which is Vx by Ix is Rs parallel with R naught divided by 1 plus Gm times Rs parallel with R naught. Okay. So this is what you can see, a circuitry, and definitely Rin is going to be so high. Input resistance of your circuitry is going to be so high here, and then output resistance is going to be pretty small, and then gain of your circuitry is close to 1. So you cannot use this as for great amplification of your signal. Okay. So we'll talk about remaining things related to this common drain amplifier in the next class.
Can you please go back to the diagram of this particular derivation?
Diagram?
Yes, sir. One turn above.
Not getting your question. Can you repeat it again?
Can you please go back to the diagram of this particular
Okay,
derivation?
okay. This one.
Yes.
Kartikeya and Hemant, no, please send me the attendance.